Hello and welcome in. My voice is just about gone, so I might be a little bit quieter. If so, I'll try to boost it in post. This week, we're going to get into the fourth and final part of proof by induction, which is differential calculus or derivatives. And all the usual things are going to be true, so the notes for this are going to be down below. We're just going to go through about 3 questions as usual. And last week was pretty quick, so we're going to try to slow down a little bit. And this topic, differential calculus, is a little bit easier than the first 3 we've done. So there's still going to be some heavy math to do for sure, but hopefully this one's a little bit less heavy or less of a cognitive load as we're working through these questions. Just like before, we're going to start off with a little investigation. And the function or the idea that we're going to investigate is the function y is equal to 2 to the x. So this exponential function. And because we're talking about differential calculus, what we're going to do is take a derivative of this function. I think it goes without saying that you will not be able to do this lesson unless you study differential calculus, so make sure you do that first. We take the derivative of 2 to the x, and following our derivative rules, this turns into 2 to the x times ln 2. And so what we might think, taking this derivative, is that this could be like a cyclical derivative where every time we take a derivative, it's kind of similar to the derivative before. So if that doesn't make too much sense, let's go ahead and take the second derivative. We'll take the second derivative written like this. And if we do that, we have to do the derivative of this 2 to the x part. ln 2 is just a constant. It's just a number. So think of it as being like a 4. When we take a derivative of a constant, it just stays there. So we put our ln 2 out front like that, and then we take the derivative of 2 to the x, and you might see where this is going. So the derivative of 2 to the x is, once again, 2 to the x times ln 2. So we see that the second derivative is ln 2 squared times 2 to the x. So when we're talking about this cyclical derivative, we kind of see that every single derivative is kind of the same as we move down to the third and fourth. We kind of expect a pattern to emerge. And so that's always going to be true with proof by induction. We do some math, we notice a pattern starts to emerge, and then we ask the question, does this pattern hold until infinity? Is this result always true? So we'll do one more. We'll say the third derivative here is, we're taking the derivative of this now. So the derivative of this first part, again, is just a constant. So this is a constant. So we'll just write that down first. We get ln 2 squared, and then we're taking the derivative of this part, 2 to the x. And we say, once again, the derivative of 2 to the x is 2 to the x times ln 2. And we get ln 2 cubed times 2 to the x. As always, this is a very simple example because we're trying to understand a concept, not explore something that might actually be interesting or we might have a real question about. The idea we're trying to illustrate here is that we can make a conjecture, or we can write a proposition. And so our propositional notation says P sub n or P of n. And for calculus, we're saying the nth derivative. So I'm going to say d to the n of y over dx to the n power. This is the nth derivative. The nth derivative of 2 to the x, from this pattern that we started to write down and take a look at, inspect, is that the derivative for this is looking like it could be ln 2 to the n power times 2 to the x, like that. Intuitively, we kind of know that this is going to be true. Like, why would it suddenly change at 1,000,001? But again, we're practicing and thinking about how can we understand proof by induction in the case or the context of derivatives. And since we already know what the result is going to be, it's a great way to kind of think about, put our focus on the proof by induction part and not so much on the calculus part. So our process here is the same process that we've always had. We take a look at the base case. We say, well, is this true for at least one of the cases? And we can say yes. So for p of 1, when n is 1, the first derivative, dy dx, and if you want to, you can put the 1 in there, but it's kind of implied, so there's a 1 there and a 1 there. We say the derivative of 2 to the x is equal to ln2 to the 1 power times 2 to the x. And again, we don't have to do too much work here. It's pretty obvious that for this first case, this is true. So the first derivative of 2 to the x is indeed ln2 times 2 to the x, and we have our base case is true, which we kind of already proved up here at the top. So in our second step of proof by induction, we try to generalize it. And so we move to our inductive hypothesis. And we're going to try to take our time writing so it's a little bit more legible. Our inductive hypothesis is written as our general case. So this is P sub k or P of k. And we're saying, can we make an assumption? Our assumption is to take our conjecture right here and state it for the general case. So we say d to the k y over dx to the k, the kth derivative of 2 to the x should be ln2 to the k power. And then this multiplied again by 2 to the x. And in keeping with our previous coloring scheme, I think our inductive hypothesis was green. Yeah, our general case was green. So let's change this to green. And let's make our base case here red, just like before as well. So we've stated our inductive hypothesis. And of course now we want to show that whenever we assume this to be true, that the case after, the derivative after this, should also be proven true. So we're going to write down our inductive step in blue. And this, of course, is our k plus 1 case, or p sub k plus 1, the case right after our k case, our consecutive case. And we say this is our goal, or our claim, what we're trying to prove. And once again, we take our k plus 1 and we just put that in. So we get d to the k plus 1 of y, well, not of y, but dx to the k plus 1. So this is the derivative right after. We're saying 2 to the x is ln2 k plus 1 times 2 to the x. So as before, everything we've done so far is exactly the same, and this is where the calculus part kind of comes in. As we saw before, we always take our assumption and we put it at the top of the screen, and we take our goal, our claim, we put it at the bottom, and we slowly try to work our way down to our goal claim using algebra. In this case, we're going to do a little bit of algebra and a little bit of calculus. So let's put our inductive hypothesis at the top to start out. So I'll put this all on a new page. And we'll grab our inductive step. And we'll put that at the bottom of the page. We won't need that much space. As we'll see, this is a pretty quick process. Maybe just to be consistent again, let's give our highlighting. So our assumption is here. And our goal in blue is at the bottom. So how can we move from a derivative to the next derivative? Well, hopefully it's pretty obvious. We need to take the derivative. So if we want to go from the second derivative to the third derivative, we take the derivative of the second derivative to give us the third derivative. So what we want to do is take d dx, the derivative of the k case. And the derivative of all this is ln2. Well, we should do this on a separate line. So first we're saying that we're taking the derivative of our assumption step. So we're taking the derivative of the kth derivative, and that is going to be equal to the derivative of ln2 to the k times 2 to the x, like that. So if we take this derivative again, it should turn into our goal, which is what we have down here. What we notice is that when we take the derivative of the kth derivative, this turns into our left-hand side. We now get the k plus 1th derivative. So this is dk plus 1 y over dx to the k plus 1. On our right-hand side is where we actually do our math. So we're taking the derivative of this whole expression. As we talked about before, some of this is a constant and some of it's a function. This might look kind of complicated, but we keep in mind that k is just a number, ln2 is just a number, so this comes out front and is not affected by the derivative. Then we take the derivative of the 2 to the x part, and just like before, we know that that's going to be 2 to the x times ln2. And so if we move our goal down a little bit out of the way, we can kind of see that this is true. It does turn into our goal. We take that ln2, we multiply it by the ln2 to the k, and that gives us, ln2 to the k plus 1. So here we get ln2 to the k plus 1, and then we get times 2 to the x. And so our k plus 1th derivative of 2 to the x is indeed ln2 to the k plus 1 times 2 to the x. And so we have our proof. Like that. So our assumption turned into our goal using algebra and by taking the derivative, both of which are rigorous. So with that being said, we can write our statement as we've seen before. And so what we can say here is that our base case P of 1 is true, and the k case, so P of k, implies the P of k plus 1 case. So whenever the k case is true, the k plus 1 case is also true. And so by mathematical induction, we can say that our statement, P of n, which we established at the beginning, we said the nth derivative is ln2 to the nth power times 2 to the x, is true for all n, where n is a part, well, we could say a part of the set Z, specifically Z plus. And that would be our final statement. And again, not a surprising result. We kind of could have guessed this at the very beginning that this would be true, but now we've conclusively and rigorously proved it using proof by induction and a little bit of calculus. All right, So as we can see, proof by induction for derivatives is pretty simple, pretty straightforward. We can make problems very difficult, but at the high school, college level, we're not going to make it too difficult. We're going to keep the functions that we explore pretty simple to, again, keep the focus on proof by induction and not on really advanced algebra or calculus. Okay, let's move down to practice problem number 1. Well, just rereading that, make sure we didn't miss anything. Base case is true. Oh, I guess we could say here, the P of K case implies the P of K plus 1 case is true, and so by mathematical induction, we can say that our statement P of n is true for all n as part of set C. All right, moving down to practice problem number 1. Practice problem number 1, we see they give us a function, 1 over 1 minus x. They give us a derivative, the nth derivative, and so what we can say is that our proposition, or our conjecture for this, P of n, is that the nth derivative of y is n factorial over 1 minus x to the n plus 1, and that's what we're trying to prove. As always, we start with our base case, our P of 1. So we take our first derivative, d1y, or you could just say dy dx. And we're saying of 1 over 1 minus x. So the first derivative of this function should be, according to this formula, 1 factorial over 1 minus x to the 1 plus 1, like that. So we simplify down, and let's see, let's make a little bit of space. I don't think we want to do that. We'll just do it over here. So we're saying the derivative here is 1 over 1 minus x to the second power. How do we know that this is true, that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared? Well, we take the derivative of 1 over 1 minus x. This requires us to do a little bit of calculus, so we're actually going to need a little bit more space. Let's move these other two down. So to prove this, we're going to take a derivative of 1 over 1 minus x. We know that the derivative of this is the derivative of 1 minus x to the negative 1 power. So that's going to require a chain rule, and what we can say is we take the derivative of the outside, which is the negative 1 power. So the negative 1 power comes down front. We keep our inside the same, and so our outside then becomes negative 2. Then we multiply by the derivative of the inside, and so we get negative 1. The derivative of negative x is negative 1. We put all that together, and we get positive 1. So the negative 1 times the negative 1 is positive 1. 1 over 1 minus x squared, like that. So we can see here that this formula that they gave us to find the nth derivative is true for the first case. And that's also pretty logical. Every time we take this derivative, we can expect that we're just going to have 1 minus x to a 1 higher power in the bottom. And there might be some things happening in the top as well as we go through. So we get that n factorial. If you're kind of curious where the n factorial comes from, try taking the second derivative and see if you can spot the pattern, and then come up with that conjecture and see if it matches theirs. Our next step is to, of course, do our general case, the inductive hypothesis, now that we've proved the base case. So let's move this down. General case is pretty quick as always, like we've seen. So we're just taking our k, we're plugging it into our statement. We're saying that the k derivative, or the kth derivative, of the function 1 over 1 minus x should be equal to k factorial all over 1 minus x to the k plus 1. And again here, we're assuming this to be true. So this is our assumption. And like we've done for all the previous parts of the series, we're going to make our assumption green. Down here in the consecutive case, our inductive step, we're going to write down our claim or our goal. So we're going to say that the next derivative, the k plus 1th derivative of 1 over 1 minus x should be, if this is true, k plus 1 factorial all over 1 minus x to the k plus 1 plus 1. And this is our claim or our goal based on what we know from the assumption. And like before, we'll make this a nice bright blue. Like we saw in the previous question, we're going to take our assumption and put it at the top, and we're going to take our goal and put it at the bottom. So we're going to need a new page. There we go. And we're going to put our goal at the top. Oops, our assumption at the top, and our goal at the bottom. All right, so like we saw before, in order to move from our assumption down to our claim, our goal, we want to use calculus. So we're saying that the derivative of our kth derivative should be the k plus 1th derivative. That's so hard to say. So dk plus 1 y dx to the k plus 1, like that. And this is taking the derivative, of course, of k factorial over 1 minus x to the k plus 1. So we're taking the derivative of the right-hand side and the left-hand side. Once again, it looks a little bit complex because we have these k's, but if we keep in mind that k is a number and it follows the rules of numbers when we do derivatives, we should be okay. So what we see here is this k factorial on top is a constant. So that's going to come out front. That will not get affected by the derivative. What we can say here is that this is 1 minus x raised to the negative k plus 1 power, like that. So if we have something in the bottom of a fraction, we can move it to the top of a fraction by making it a negative power. So what we see here is just like what we saw before in our base case. We're doing the chain rule. It looks more complicated because there's a k here, but it's really just 1 minus x raised to a number. So to take this derivative, we want to do the derivative of the outside first. So we take our power, negative k plus 1, like that. We bring it down front. We keep our inside part the same. And then we take this power here and we raise it. Well, we subtract 1 away from it. So that's going to be negative k plus 1 and then minus a 1. Then we multiply by the derivative of the inside, which is negative 1, like that. So that's the derivative. Now we just need to simplify and clean it up a little bit to get down to our claim goal. Let's move this down a little bit and move our goal down just a tad. All right, So this k factorial is out front. We'll leave that there for now. Right here, we now have a negative and a negative. Like we saw before, those negatives cancel out, and so we just get k plus 1 here, like that. And then here we get 1 minus x. And up here, we can kind of see that this is all negative. So we have negative k, negative 1, and then another negative 1. So this is negative k minus 2, like that. So we just want to simplify again. Using what we know about factorials, k factorial, maybe we can do it over here, is equal to k times k minus 1 times k minus 2, and so on. K plus 1 factorial is this whole previous factorial, just with k plus 1 added on. So now we have a k plus 1 out front, like that. And so you can probably see where this is going. If we have k factorial times k plus 1, that's going to change into k plus 1 factorial. So we get k plus 1 factorial up front, which is a good sign. And we can see that in our goal right there. And then the second part of this is we have our 1 minus x to all of this in the negative power. So we need to rewrite it a little bit and move it back into the denominator. Using exponent properties, we know that negative exponents turn into positive exponents if they're moved into the bottom. So we're going to get 1 minus x to the positive k, and now the positive 2, like that. And if you want to write it one more time, we can say that this is k plus 1 all factorial over 1 minus x, k plus 1, like that. And so we can say that the k plus 1th derivative of, well, we've run out of space. Let's move this all down a little bit. Of 1 over 1 minus x is equal to k plus 1 over 1 minus x to the k plus 1, and this is factorial. And that is our proof. So starting with our assumption, we used calculus and algebra, and it changed into our consecutive case. So we basically proved that our k case and the case right after get proved together, and that's enough to say that this pattern is going to hold until infinity, or for forever, for all positive integers. So we kind of wrap things up by putting in our statement, and we can copy that one from before, since it's always going to be basically the same. Let's see. We set up here. We proved our base case. We proved our k case, our general case, and we proved the consecutive case, the case right after. Because the general case implies that the case after is true, we have enough proof to say that this is true, this statement p of n is true for all n in the set of positive integers. All right, moving down to practice problem number 2. This time we're taking a derivative of a function. Well, all of these functions kind of have a pattern to them. That's why we're looking at them. But we're taking a look at a pretty common derivative that repeats a exponential function with base e. So if you take the derivative of e dx, it turns into e dx. And so we can kind of intuitively sense that this one's probably going to have a pattern that holds as well. Once again, they've given us the pattern. So they're saying that the nth derivative of this function is equal to this. And so this is our proposition, it's our conjecture, our p of n. We start off with our base case, as always, and we say, well, what about when n is 1? This would be our proposition with n equal to 1. We'd say this is our first derivative. So we can say the first derivative of x e to the 2x, according to this proposition or formula, is 2 to the 1, which is 2, times x. We can just say 2x, plus n, which is now 1, 2 to the 1 minus 1 is 0. And all of this is multiplied by e to the 2x. So we're saying the first derivative of x times e to the 2x is going to be 2x times e to the 2x, like that. Is this true? Well, we need to take the derivative using our derivative rules. So over here we take the derivative of x e to the 2x. Looking at this, hopefully what comes to mind is the product rule, because we have two functions that are multiplied together. So the product rule says we take the derivative of the first, derivative of x is 1, keeping the second one the same, and then we add that to keeping the first one the same, multiplying by the derivative of e to the 2x. The derivative of e to the 2x it requires the chain rule. So we know that the outside function is e. The derivative of e is the same. We keep the inside the same. The 2dx keeps that the same. And we multiply by the derivative of 2x, and that gives us 2, like that. So we simplify that, and we get e to the 2x plus 2x e to the 2x, like that. And we see that these do not agree, and maybe you can see what mistake we made. If not, pause it and take a look. Up here, our 2 to the 0 is not 0. It's actually 1. And so what we should have gotten here up above is 2x e to the 2x, and then we also should have gotten 1 times e to the 2x is e to the 2x, like that. We can see that these two now match, so our proposition for the base case is true, and we can move on to the general case. In the general case, we do what we always do, which is to take our n and replace it with k. So we're going to say here that the kth derivative I don't know if there's a way to say that. If someone knows, put it down in the comments. D to the k of y, I feel like that's not correct. Dx to the k. So the kth derivative of our function x e to the 2x. According to this proposition, is that it should be 2 to the kx and plus k2 to the k minus 1, and then all of this is multiplied by e to the 2x. This, of course, is our assumption, so we mark it as such. And as always, we're going to put that in green. And then we move down to our consecutive case, our k plus 1 case. And we just repeat this process, plug in k plus 1. So we say d to the k plus 1 of y over dx to the k plus 1, the k plus 1th derivative of x e to the 2x is equal to 2 to the k plus 1 times x plus k plus 1 2 to the k plus 1 minus 1 e to the 2x. And this is our goal or our claim to be proven based on our assumption. And as always, this is in blue. And make sure that this one's in green. And just making sure we didn't make any mistakes when we're plugging in. So 2 to the k plus 1 x, k plus 1 times 2 to the k plus 1 minus 1 e to the 2x. All right. As always, we're going to take our assumption and put it at the top. That's where we're going to start. And then we're going to put our goal at the very bottom. Oh, that should not have come as well. Let's get rid of that. All right, grabbing our goal. Oh, I see what happened. Let's try that one more time. And we're going to put that down at the bottom as always. Just like we saw before with the previous two questions, we're going to take a derivative of the assumption, and that will give us the consecutive derivative. So here, once again, we're going to say the derivative of the kth derivative should be equal to the k plus 1th derivative. Like that. So our right-hand side immediately changes into our goal or our claim. On the right-hand side, that means we're taking the derivative of our right-hand side as well. So we're taking the derivative of 2 to the k times x plus k. Did we lose something? I feel like we lost something maybe. Oh, there should be a little multiplication there. Maybe not necessary. K times 2 to the k minus 1 e to the 2x. As before, just keep in mind our k's are just numbers, so they won't get affected by the derivatives as we kind of work through this. This one does look a little hairy, but try not to get scared by it. It's just doing derivatives like we always have. What we take a look at first is that some parts of this are constants and some parts of this are functions. So we notice here, all of this is a constant. Will not be affected by a derivative. This over here will get affected by the derivative. And then finally, our e to the 2x will get affected by the derivative. We could multiply out here and then take our derivative. That might be better. Or we could consider the whole parentheses to be the first part, and then the e to the 2x is the second part. I think we can leave it as it is. So I don't think we have to multiply out. We can save ourselves a little bit of work. But if you have a preference, you want to multiply it out first, it makes it look easier, by all means do that. So what we can see here is, again, we have two things multiplied together, and so that's going to require a product rule. So we're going to take the derivative of the first and then keep the second the same. So since we're keeping the second the same, we'll write that down as e to the 2x. And over here, we're going to keep the first part the same. And so we can go ahead and write that part down. And then derivative of the second. The derivative of e to the 2x is pretty easy, so let's go ahead and do that. It's e to the 2x times 2. So this will be the second half of our product rule. And then over here, we have to take the derivative of all of this. 2 to the k x plus k times 2 to the k minus 1. So we're taking the derivative of that. So if you're doing product rule and it's really complicated like this, it might help to kind of write it out first. If you want to, maybe we should do this as well. We'll say, instead of doing the derivative here, we'll write this as the derivative of that. So the product rule says we take the derivative of the first, multiply by the second, and then keep the first one the same, multiply by the derivative of the second. Okay, so our next step, of course, is to take the derivative of this. Our first part here is 2 to the k. It looks complicated, but it's just a constant, so 2 to the k stays there. The derivative of x is 1, so we just get 2 to the k like that. This right here is a constant, this whole thing, so that disappears, and we get just a 0 there, like that. All that's multiplied, e to the 2x. In the second part of our product rule, we take this part and we keep it the same, so we get 2 to the k times x plus k times 2 to the k minus 1. And then, like we saw before, this second derivative is not too bad. It's e to the 2x, derivative of the outside, keeping the inside the same, and then multiplying by the derivative of the inside, which is 2x, which is 2, like that. So let's see. I guess we didn't do this in previous questions, but to maybe be thorough with our notation, what we should say here is that this left-hand side is x e to the 2x. So we're taking the derivative of the kth derivative of this function. And so down here, this is the k plus 1th derivative, x e to the 2x, like that. Let's move up real quick and correct that in our previous questions as well. So in this previous one, here we should have the same thing. We should have our function out front as well. So this is the 1 over 1 minus x function, or the k plus 1th derivative of 1 over 1 minus x, like that, which comes down to that. And in our very first case as well, I think we did the same thing. Yeah, we did. So this is not super important, but if you're looking at the notes, the copy of the notes, they will have the correct notation in them. So this one is 2 to the x, 2 to the x, and 2 to the x. Okay, jumping all the way back down to practice question number 2. We're going to take all of this and move it down, as we always do. And we're going to continue the process of simplifying this kind of long, messy derivative. What we can say here is that we have 2 to the k times e to the 2x. And then over here, we have 2e to the 2x multiplied by 2 to the k x, maybe keep that there, k times 2 to the k minus 1, like that. It's kind of hard to see where we might want to go, but if we take a look at our goal down here, we see that the e to the 2x is kind of factored out front. So that gives us a guide of what to kind of do next in our algebra. We can say, well, let's factor out an e to the 2x as our first step. If we factor out an e to the 2x, we get a 2 to the k left over. So we get 2 to the k there, like that. And then for our second one, if we factor out an e to the 2x from this thing, we get a 2 left over, and then everything inside the parentheses is still there. So, not really difficult math, but stay organized. There's lots of places to make little small math errors with this many moving parts. So we feel like we're getting closer. We keep comparing it against our goal, our claim down below. We see that we have an e to the 2x, so that looks good. We have a 2 to the k here, and we have a 2 to the k there, and we have an x here and an x there. And what else do we have? Well, this one here, needs to turn into this there. So not super easy to see where we should go next. What we could probably say is that in our goal claim, this is 2 to the k. So k plus 1 minus 1 is 2 to the k. So we're going to need to end up with a 2 to the k someplace. And it looks like we have a 2 to the k here. It's just not multiplied by anything. And then over here we have another 2 to the k, and that's multiplied by our x. And we need that to be a 2 to the k plus 1. So let's start with this one here. That one looks easy to do. We can say that if we multiply this 2 in, we get e to the 2x out front. We get 2 to the k plus 2 times 2 to the k. And, well, we'll do it in another step. Keep it as, what's the word? Keep it as obvious as possible what we're trying to do. So we get 2 times 2 to the k, and then we get plus 2 times k times 2 to the k minus 1. And maybe you can now start to see where this is going, if you already didn't see where this is going from before. So when we multiply those 2's in, we can again use exponent properties to combine the powers and give us the terms that we're looking for. So taking our goal, moving it out of the way, we can see here, ooh, that's not good. Let's, we're gonna need a new page for that. I have a feeling it's gonna grab, yeah. Oh well, okay. We will make do. So we lost our color and we also lost our D. Let's put that back in. So this goal, we're just trying to move down to the bottom of the screen. Okay, so back to where we were. What we can see here is that we have e to the 2x outside. Inside we have 2 to the k, and now we have 2 to the k plus 1 here, like that. And then over here we have 2 times 2, so that's going to be k times 2 to the k minus 1 plus 1. We're combining these powers in the exponent, so this is just going to be 2 to the k, like that. And now we see that there's a lot of similar terms here, so we get e to the 2x. We have a 2 to the k and a 2 to the k, so we factor out a 2 to the k from this term, this term and this term. And so what we're going to get here is 1 from this first term, and we're going to get a k from this one. So we get 2 to the k and then 1 plus k, or maybe we can, well, we'll leave it like that. We can see that that turns into k plus 1. And then finally we have over here 2 to the k plus 1, and then close parentheses. So kind of looking down here at our goal claim, we're just about done. All we need to do is rewrite things a little bit. So here at the beginning we have 2 to the k plus 1 times x. We've lost our x someplace, so we're going to have to go back into our steps and see where we made a mistake. And then we have our k plus 1 times 2 to the k, which is the same thing as k plus 1 minus 1, like that. And then we have e to the 2x out here, like that. Okay, this happens pretty often, so I'm glad this happened as we were working through this question. What we can see is that this x disappeared somewhere in one of our previous steps. If we go back up here, we notice that this one had an x on it. And when we move down to this step here, this 2 times 2 to the k, we dropped our x off, so there should be an x there. That one would give us a, let's see, x here. And so this one would have an x there, and then it shows up there. and that gives us our final result. The great thing about proof by induction is that they only give you questions that are going to be proven true. So if you get to your goal claim and there's something missing, it's pretty easy to go back through your work and find the small math error. So you basically always have the answer for you at the end, which is pretty nice. Okay, that brings us to the end of practice question number 2, and also the end of this lesson. As we can kind of see, proof by induction for differential calculus is not too bad. The math is pretty straightforward, and that's because if we took more complicated functions, doing proof by induction with calculus would get really difficult really quickly. So what we can see here, again as a recap, is that for differential calculus, derivatives a lot of times have a pattern that emerges as we take successive derivatives. And so proof by induction is a great way to prove that pattern is true for all the derivatives. Why would you need to take multiple derivatives? When you get into Maclaurin and Taylor series, that's one possible application. And there might be more. If you have any that you can think of, put them down in the comment section. I would love to read and see those. So we see here that proof by induction for derivatives, very similar to everything we've done in the first 3 parts of this series. We do our base case, we write down our assumption, and now the only new part is that to go from our assumption to our inductive step, our goal claim, is we take a derivative, and then we simplify the algebra. So we kind of saw that here on our very first question, pretty simple. And then we repeated this process for functions that were a little bit more complicated. So we had a rational function here, and then finally we moved down to an exponential function, which required a lot of product rule. So we had this exponential function here, and we wrote our base case, our assumption, and our goal, and then we saw that this one got pretty complicated with a lot of intermediate steps, but mostly just algebra, and our goal will always show us where we need to end up eventually. So we kind of have a guide taking us to our last step. All right, if you have any questions, if there's any mistakes, anything you want to mention, put them down in the comments, and then I will see you next week.